7. Powerful function of inductor and its application. An inductor is a passive electrical component that stores energy in a magnetic field when electrical current passes through it. Inductors have various applications in electrical and electronic circuits, where their unique properties can be harnessed in different ways. Here are 7 powerful functions of inductors and their applications. Energy storage in inductors. Function. An inductor stores energy in the form of a magnetic field when current flows through it. This energy is stored based on the inductor's ability to oppose changes in current, which is described by its inductance. The energy stored in the magnetic field can be released back into the circuit when the current flow decreases or is interrupted. Key points. The stored energy is proportional to the square of the current flowing through the inductor. When the current increases, the magnetic field around the inductor expands, storing more energy. When the current decreases, the magnetic field collapses, releasing the stored energy. Applications of energy storage in inductors. Switching power supplies, DC-DC converters. Application. In switching regulators, inductors store energy during the on phase of the switch and release it during the off phase. This allows the conversion of DC power from one voltage level to another with high efficiency. Example. Buck converters use inductors to step down voltage, while boost converters use them to step up voltage. Transformers. Application. Inductors are used in the primary and secondary coils of transformers. The energy stored in the magnetic field of the primary coil is transferred to the secondary coil through electromagnetic induction, allowing for voltage transformation. Example. Power distribution systems use transformers to step up voltage for transmission and step it down for local use. Flyback converters. Application. In flyback converters, the inductor, often combined with a transformer, stores energy when the switch is closed and releases it when the switch is opened, providing power to the load. Example. Flyback converters are commonly used in isolated power supplies for applications such as televisions and power adapters. Uninterruptible power supplies, UPS. Application. Inductors in UPS systems store energy during normal operation and release it during power outages to maintain a stable power supply. Example. A UPS for a computer system might use an inductor to help maintain power during a brief blackout. Electric vehicles, EVs. Application. Inductors are used in the power electronics of electric vehicles to store and manage energy during the conversion of power between different components, such as between the battery and the motor. Example. In EV charging circuits, inductors help manage energy flow and efficiency during charging and discharging. Inductors' ability to store energy in magnetic fields makes them vital components in modern electronic systems, enabling efficient energy transfer and management. Filtering with inductors. Function. Inductors can act as filters by allowing low-frequency signals or DC signals to pass through while blocking or attenuating high-frequency signals. This behavior is due to the inductor's property of increasing impedance with increasing frequency. In other words, inductors resist changes in current more effectively at higher frequencies, making them useful as filters in electronic circuits. Key points. At low frequencies, the impedance of an inductor is low, so it allows current to pass. At high frequencies, the impedance increases, making it difficult for current to pass. Inductors are commonly used in low-pass filters, where they block high-frequency signals and allow low-frequency signals to pass. Applications of filtering with inductors. Power supply filtering. Application. Inductors are used in power supply circuits to filter out high-frequency noise or ripples from the output. This helps ensure a smooth DC voltage is delivered to sensitive electronic components. Example. In a regulated DC power supply, an inductor in conjunction with a capacitor can form an LC filter to reduce the ripple voltage after rectification. Audio systems crossovers. Application. Inductors are used in audio crossover networks to filter out high frequencies, directing low-frequency signals to woofers and subwoofers. This helps optimize the performance of different speakers in a sound system. Example. In a speaker system, an inductor may block high frequencies, allowing only bass frequencies to reach the woofer. RF radio frequency filtering. Application. Inductors are used in RF circuits to block or attenuate unwanted frequencies while allowing desired signals to pass. This is essential for maintaining signal integrity in communication systems. Example: in a radio receiver, inductors are used in combination with capacitors to create tuned circuits that filter out all but the selected radio station. AC line filters. Application: inductors are used in conjunction with capacitors to filter AC power lines, blocking high-frequency noise generated by switching power supplies or other electronic devices. This helps protect sensitive electronics from electromagnetic interference, EMI. Example: AC line filters are commonly used in computer power supplies and home appliances to prevent noise from entering the power line. Switch mode power supplies, SMPS. Application: in SMPS circuits, inductors are used to filter out switching noise from the output. Since SMPS circuits operate at high frequencies, inductors help to smooth out the voltage and reduce electromagnetic interference. Example: inductors in an SMPS circuit help ensure that the output voltage remains stable despite the high-frequency switching operation. Signal conditioning. Application: inductors are used in signal conditioning circuits to filter out noise from analog signals before they are processed by digital systems or sensitive analog circuits. Example: in instrumentation systems, inductors help filter out noise from sensor signals to ensure accurate measurements. Chokes for EMI suppression. Application: common mode chokes are specialized inductors used to suppress high-frequency electromagnetic interference on power lines and signal cables by blocking high-frequency noise without affecting the desired signals. Example: EMI suppression chokes are used in USB cables, Ethernet cables, and other data cables to reduce interference from external sources. Inductors are essential components in various types of filters, helping to maintain signal integrity, reduce noise, and ensure that electronic systems function as intended in a wide range of applications. Choking with inductors. Function: an inductor used as a choke restricts or chokes high-frequency alternating current, AC, while allowing direct current, DC, or lower-frequency AC to pass through. This behavior is due to the inductor's increasing impedance at higher frequencies. Chokes are primarily used to block high-frequency signals, especially in situations where unwanted noise or interference needs to be filtered out. Types of chokes. Common mode choke filters out noise or interference that is common to both lines of a pair of conductors, often used in EMI suppression. Differential mode choke blocks unwanted high-frequency signals in a single conductor or pair while allowing the desired signals to pass. Key points. Impedance. As frequency increases, the impedance of the inductor also increases, making it an effective choke for high-frequency AC signals. DC path. Inductors present very little resistance to DC, so they allow DC signals to pass through with minimal loss. Applications of choking with inductors. Radio frequency, RF circuits. Application: choke inductors are used in RF circuits to block high-frequency signals that could interfere with the proper functioning of the circuit. They allow DC biasing while isolating different sections of the circuit from high-frequency noise. Example: in RF amplifiers, chokes are used to prevent RF signals from reaching power supply lines, where they could cause unwanted interference. Electromagnetic interference, EMI, suppression. Application: common mode chokes are widely used to suppress EMI in power lines and signal cables by blocking high-frequency noise that is common to both conductors without affecting the normal operation of the system. Example: in power supplies for computers and other electronics, common mode chokes are used to reduce noise from switching components, preventing it from radiating through power lines and causing interference with other devices. Power supply filtering. Application: chokes are used in power supply circuits to block high-frequency noise generated by switching power supplies and other high-frequency devices, ensuring a clean DC output. Example: in a switching power supply, a choke inductor is placed after the rectification stage to block high-frequency ripple from the output voltage. Audio systems, signal conditioning. Application: in audio systems, choke inductors can filter out high-frequency noise from audio signals, preserving the clarity of the sound. Example: Chokes are often used in analog audio circuits to prevent high-frequency interference from affecting the audio quality. Fluorescent lamps and HID lighting. Application. In fluorescent and HID, high-intensity discharge lamps, chokes are used to limit the current passing through the lamp, preventing it from drawing excessive current once it is ignited. Example. In fluorescent lamp ballasts, the choke inductor regulates current flow to ensure consistent operation of the lamp and extend its lifespan. Motor drives. Application. Chokes are used in motor drive circuits to suppress noise and harmonics generated by variable frequency drives, VFDs, or other switching devices. This helps to reduce electromagnetic interference and protect the motor and connected equipment. Example. Line chokes are often used in industrial motor drives to reduce the impact of harmonics and improve power quality. Power line chokes, PFC circuits. Application. Power factor correction, PFC. Circuits use chokes to filter out high-frequency noise and harmonics from power lines, improving the efficiency and stability of power distribution systems. Example. Chokes in PFC circuits help to improve the overall power factor of electronic devices, reducing the load on the electrical grid and minimizing energy losses. Choke inductors are essential in circuits where it is necessary to filter out high-frequency noise or unwanted signals while allowing desired low-frequency signals, or DC, to pass through. This makes them vital components in power supplies, RF systems, motor drives, and EMI suppression. Resonance with inductors. Function. Resonance occurs when an inductor and a capacitor are combined in a circuit such that their reactances cancel each other out at a specific frequency. This results in a condition where the circuit can oscillate at its natural frequency with minimal energy loss. The resonant of a simple LC, inductor capacitor, circuit is given by the formula. At resonance, the energy oscillates between the electric field of the capacitor and the magnetic field of the inductor, making the circuit highly sensitive to signals at the resonant frequency. Key points. Resonance occurs when the inductive reactance, 等于 2 pi x L equals 2 pi FL equals the capacitive reactance, 等于 1, 2 pi x C, 等于 VOP 1. At the resonant frequency, the circuit exhibits minimal impedance and can sustain oscillations with minimal energy loss. Resonant circuits are highly selective, allowing only signals at or near the resonant frequency to pass through or be amplified. Applications of resonance with inductors. Radio tuners. Application. LC circuits are used in radio tuners to select and amplify a specific frequency from a range of broadcast frequencies. By adjusting the values of the inductor and capacitor, the tuner can be set to resonate at a desired frequency, allowing it to pick up a particular radio station. Example. AM and FM radio receivers use resonant LC circuits to tune into specific frequencies while rejecting other signals. Oscillators. Application. LC oscillators generate continuous oscillating signals at a specific frequency by using resonance. The resonant frequency determines the output frequency of the oscillator, which is essential for communication systems and timing circuits. Example. Crystal oscillators in watches, microcontrollers, and communication devices use LC circuits to generate precise clock signals. Filters. Application. Resonant LC circuits are used in bandpass and bandstop filters to allow or block specific frequency ranges in communication systems, audio equipment, and signal processing applications. Example. A bandpass filter in a wireless communication system allows only the desired frequency range to pass through while filtering out all other signals. Resonant power transfer. Application. Inductors are used in wireless power transfer systems, such as inductive chargers for electric vehicles or mobile phones. Resonant inductive coupling allows efficient transfer of power at a specific frequency over short distances. Example. Wireless charging pads for smartphones use resonant inductive coupling to transfer energy without physical connectors. RF identification, RFID systems. Application. Resonant circuits are used in RFID tags and readers to communicate by tuning to the same resonant frequency. The tag uses resonance to absorb and retransmit signals to the reader, allowing for data exchange. Example: RFID systems and access control, inventory management, and contactless payment systems use resonance for efficient communication between tags and readers. Induction heating. Application: resonance circuits are used in induction heating systems, where high-frequency currents are used to induce eddy currents in a conductive material, generating heat. The resonant frequency ensures efficient energy transfer for heating applications. Example: induction cooktops and industrial induction heaters use resonance circuits to generate high-frequency currents for heating metal objects. Magnetic resonance imaging, MRI. Application: in MRI machines, resonance between radio frequency signals and the magnetic fields generated by inductors in the system is used to excite hydrogen atoms in the body, allowing for detailed imaging of soft tissues. Example: the resonance circuits in MRI scanners are tuned to specific frequencies to produce detailed images for medical diagnostics. Resonance is a powerful phenomenon that enables the precise selection and amplification of signals, efficient power transfer, and energy conversion in various applications. Inductors, in combination with capacitors, play a crucial role in achieving resonance in these systems. Inductive sensing with inductors. Function: inductive sensing leverages the properties of inductors to detect the presence, proximity, or movement of metallic objects. This sensing method relies on the principle that a changing magnetic field induces eddy currents in conductive materials, which in turn affect the inductance of a coil. By monitoring changes in inductance, inductive sensors can detect nearby objects without direct physical contact. Key points: proximity detection. Inductive sensors detect changes in inductance caused by nearby metallic objects, making them ideal for proximity sensing. Non-contact sensing. Since the sensing is based on magnetic fields, inductive sensors can operate without direct contact with the object being detected. Robustness. Inductive sensors are resistant to environmental factors such as dust, dirt, and moisture, making them reliable in harsh conditions. Applications of inductive sensing with inductors. Proximity sensors. Application: inductive proximity sensors are used in industrial automation to detect the presence or absence of metal objects. These sensors are commonly used for position detection, counting, and as limit switches in machinery. Example: inductive proximity sensors are often found in conveyor systems to detect the presence of metal parts for sorting or quality control. Metal detectors. Application: inductive sensing is used in metal detectors to detect the presence of metal objects by sensing changes in the magnetic field caused by the metal. These detectors are widely used for security, archaeology, and treasure hunting. Example: airport security metal detectors use inductive sensing to detect metallic objects on individuals as they pass through the scanner. Inductive encoders. Application: inductive encoders use inductive sensing to determine the rotational position of a shaft. These encoders are used in applications where precise positioning and high reliability are required, such as in robotics, automation, and aerospace systems. Example: an inductive encoder might be used in a robotic arm to precisely measure its rotational position, ensuring accurate movement and control. Automotive sensors. Application: inductive sensors are used in various automotive applications to detect the position of metal components, such as in anti-lock braking systems, ABS, camshaft position sensors, and gear shift position sensors. Example: inductive sensors in an ABS system detect the rotational speed of the wheels, providing feedback to the braking system to prevent wheel lockup. Inductive flow meters. Application: inductive flow meters measure the flow of conductive liquids by sensing the induced voltage in a fluid as it passes through a magnetic field generated by the inductors in the sensor. These flow meters are commonly used in industries where accurate liquid flow measurement is essential. Example: inductive flow meters are used in water treatment plants to measure the flow rate of treated water. Smartphones and wearable devices. Application: inductive sensing is used in some smartphones and wearable devices to detect gestures, proximity, or movement without physical contact. This allows for touchless interaction with the device. Example: some smartphones use inductive sensors to detect when the phone is near a user's ear, automatically turning off the screen during a call. Inductive proximity cards, RFID. Application. Inductive sensing is used in RFID, radio frequency identification, systems, where an inductive coil in the reader interacts with a similar coil in the RFID tag to exchange data wirelessly. These systems are used for access control, inventory management, and contactless payments. Example: proximity cards used for access control in buildings employ inductive sensing to communicate with the card reader when brought close to it. Inductive sensing provides a non-contact, reliable, and robust solution for detecting metal objects, measuring positions, and enabling smart sensing in various industrial. Current limiting with inductors. Function. Inductors are used to limit the amount of current flowing through a circuit by opposing sudden changes in current. This is due to an inductor's ability to generate a back electromotive force, EMF, in response to changes in current. When a current through an inductor increases or decreases rapidly, the inductor opposes this change by inducing a voltage in the opposite direction, thereby limiting the rate of current change and preventing current spikes. Key points. Back EMF. When current changes rapidly, the inductor generates a back EMF, which opposes the change and limits the current. Gradual current change. Inductors prevent sudden surges of current, allowing it to change more gradually over time, which protects components in the circuit. High efficiency. Inductors can limit current with minimal power loss, as opposed to resistive methods that dissipate energy as heat. Applications of current limiting with inductors. Inrush current limiting. Application. Inductors are used to limit inrush current when electrical devices are first powered on. Inrush current can damage components or trip circuit breakers if not controlled. Inductors help reduce the peak current when the device is switched on by opposing the sudden influx of current. Example: in power supplies, inductors limit the inrush current when the supply is first connected to the power source, protecting components like transformers and capacitors. LED drivers. Application. Inductors are used in LED driver circuits to regulate the current flowing through LEDs, ensuring they operate within safe current limits. LEDs are sensitive to overcurrent, and inductors help to prevent current spikes that could damage the LED. Example: in an LED driver circuit for lighting, an inductor helps limit the current and prevent damage to the LED during operation. Motor start protection. Application. Inductors are used in motor circuits to limit the initial surge of current when the motor is started. This protects the motor windings and the power supply from damage due to high starting currents. Example: in industrial motors, inductors limit the starting current to prevent damage to the motor and extend its lifespan. Battery chargers. Application. Inductors are used in battery charging circuits to limit the current delivered to the battery, ensuring that the battery is charged safely and efficiently without overheating or overcharging. Example: in a smartphone charger, an inductor helps regulate the current supplied to the battery, preventing excessive current flow that could damage the battery or reduce its lifespan. Power supply protection. Application. In power supply circuits, inductors are used to limit current to prevent overcurrent conditions that could damage components or cause overheating. This is particularly important in switching power supplies, where current can fluctuate rapidly. Example: in a DC-DC converter, an inductor limits the current to protect sensitive components from sudden surges or fluctuations in power. Fuseless overcurrent protection. Application. Inductors can serve as a form of overcurrent protection in circuits where fuses or other protection devices are impractical. By limiting current naturally, inductors reduce the need for mechanical protection devices in some applications. Example: in low-power circuits, inductors are used to limit current without the need for fuses or circuit breakers, providing a simpler and more reliable form of protection. Inductive ballasts. Application. Inductive ballasts in lighting systems, such as fluorescent lamps, limit the current to the lamp after it has ignited, preventing excessive current flow that could damage the lamp or reduce its efficiency. Example: fluorescent light ballasts use inductors to limit the operating current to the lamp after the initial startup surge. Inductors are crucial for current limiting in various circuits, ensuring that current flows smoothly and preventing potentially damaging spikes or surges. They offer a robust, energy-efficient solution for protecting sensitive components and improving the reliability of electronic systems. Energy transfer in transformers with inductors. Function. In transformers, inductors are used to transfer electrical energy from one circuit to another through electromagnetic induction. A transformer consists of two or more coils of wire, inductors, wound around a shared magnetic core. When an alternating current, AC, flows through the primary coil, it generates a varying magnetic field. This changing magnetic field induces a voltage in the secondary coil, transferring energy between the two circuits without direct electrical connection. Transformers are essential for stepping up or stepping down voltage levels in power transmission and distribution systems. Key points. Mutual induction. The varying current in the primary coil induces a corresponding voltage in the secondary coil due to the shared magnetic field. Efficiency. Transformers can transfer energy with very high efficiency, often above 95%, making them ideal for large-scale power transmission. Voltage transformation. By adjusting the ratio of turns between the primary and secondary coils, transformers can increase, step up, or decrease, step down, the voltage. Applications of energy transfer in transformers. Power transmission. Application. Transformers are used in power grids to transfer electrical energy from power plants to homes and businesses. High-voltage transformers step up the voltage for long-distance transmission, minimizing energy losses. At the receiving end, step-down transformers reduce the voltage to safe levels for household and commercial use. Example: high-voltage transformers are used in substations to step up the voltage for transmission over long distances, reducing energy loss in the power lines. Electrical isolation. Application. Isolation transformers transfer energy between circuits while providing electrical isolation. This prevents direct electrical contact between the primary and secondary circuits, enhancing safety and protecting sensitive equipment from electrical faults. Example: isolation transformers are used in medical devices to protect patients from electric shocks by isolating the device from the power grid. Voltage regulation. Application. Auto transformers and tap-changing transformers are used in power systems to regulate voltage levels, ensuring a stable supply of electricity to consumers. By adjusting the transformer's output, voltage fluctuations can be minimized, improving the reliability of the power supply. Example: tap-changing transformers are used in substations to maintain a consistent voltage level on the power grid, even during periods of fluctuating demand. Audio transformers. Application. Audio transformers are used in audio systems to transfer signals between different stages of the circuit, matching impedances and isolating sections of the system. They help in maintaining signal integrity and reducing noise. Example: audio transformers are used in professional audio equipment, such as microphones and amplifiers, to isolate and transfer audio signals without introducing noise or distortion. Pulse transformers. Application. Pulse transformers are used in digital circuits to transfer fast pulse signals between different parts of a circuit. They are designed to handle high-speed signals while isolating the transmitting and receiving circuits. Example: pulse transformers are used in Ethernet transceivers and communication devices to transfer data signals between circuits with high-speed accuracy. Induction heating. Application. Transformers are used in induction heating systems to transfer energy to a workpiece by inducing eddy currents, which generate heat. The transformer steps up the current to high levels, enabling efficient heating of metals for industrial processes. Example: in metal processing, transformers and induction heaters are used to efficiently heat metal parts for forging, welding, or annealing. Wireless charging. Application. Transformers are used in wireless charging systems to transfer energy wirelessly between the charging pad, primary coil, and the device, secondary coil. The energy is transferred via electromagnetic induction, allowing for the wireless charging of smartphones, electric vehicles, and other devices. Example: wireless charging pads for smartphones and electric vehicles use transformers to transfer energy across an air gap, charging the device without a physical connection. Summary: transformers, which are based on the principle of inductive energy transfer, play a vital role in electrical power systems, electronic devices, and industrial applications. By transferring energy efficiently through electromagnetic induction, transformers enable voltage regulation, electrical isolation, and power distribution on a global scale, making them fundamental to modern electrical infrastructure. Conclusion: inductors play a crucial role in a wide range of applications across electrical engineering and electronics. From energy storage and filtering to resonance and sensing, their properties make them essential components in both simple and complex circuits.